design, there are a couple of terms that you kind of have to know in order to be able to successfully answer all of the questions. So the first thing that we're going to talk about is whenever you are describing the people who are having the experiment performed on them, one thing I'll say before we get there is if you have an observational study, that means there are no treatments. Typically, you're only doing a sample survey. So you're not necessarily changing anything about what the person, place, or thing would normally do. You are simply just observing and asking them questions. So when you go to experiments, you have people, places, things that you are changing, and you are trying to see by making this change, is there a response? And so when it's just regular, like batteries, and I'm testing plants and things like that, they are experimental units. When it is people, typically they will refer to them as subjects. Now that's not the biggest, like if you say experimental units and you're talking about a human being, it's not the end of the world, but that's just how they're going to kind of use the terms on the AP exam. The next thing that we kind of look at is confounding variables. So sometimes when you're testing something, and I'm going to use plants as an example, if I want to see, does this new fertilizer help plant growth, I don't change anything else. I'm just changing the fertilizers. I have other variables that are in play with how a plant grows that could be causing a response. If one plant is getting more sunlight than another or more water than another, that could affect the plant growth, and it's not something that I accounted for, so that could potentially be a confounding variable. In the next lesson, we will talk about confounding versus lurking. For now, all you have to think about for this is it's something that I did not account for that is making it look like there's a relationship between the explanatory and the response. Now, for some terms that you're probably familiar with, which is why we don't spend a ton of time on them, if you are doing an experiment, oftentimes it's beneficial to have a placebo. And basically that's like a dummy experiment where it looks exactly like what the treatment would be. However, there's nothing being applied. In medical things, it's usually like a sugar pill that's designed to look like the drug that they are taking, but it has no effects whatsoever. With the placebo, there's a couple of things that kind of happen from that. You could potentially have the placebo effect where someone is taking the medicine, there's nothing that's going to be changing, but because of the fact that they're taking something, they start to see results. So that would be the placebo effect. And then to fix the placebo effect, typically, we try to blind our experiments. So by that, I mean, we are going to, for single blind studies, that means that the person, the subject that the experiment is being done on, does not know what they are receiving. They all look the same, they have no idea, and that's just hopefully to prevent them from kind of making up effects in their head. And then the double-blind study is when both the person, the experiment, the unit, the subject, doesn't know what's going on, but also the evaluator doesn't know what's going on. So a lot of the times with doctors, when they come in, they start taking blood pressure and all of those things, you don't want them to have like leading questions that will have the person think like, oh, well, they're asking me if I'm sure I feel okay, so maybe I do have the medicine, so maybe I should be feeling better. You want to have like a neutral third party be the one to evaluate so that you get accurate results. So that should all be kind of familiar. I'm sure you've heard those terms before in one of your many science classes, but it still applies in experiments and stats. Now, for experimental design, there are a couple of things that you have to have. There's 4 elements that have to be a part of your experimental design in order, and the goal of this is to establish cause and effect. So if I want to be able to say that my explanatory variables are causing this response, I have to have these 4 things. The first thing that I have to have is comparison. I can't just go out and test my new fertilizer and not compare it to something. So if I gave all of my plants the new fertilizer and I'm like, well, yeah, my plants are growing, great. But I didn't actually compare it to the old fertilizer, which probably would have had the same results. So whenever you are doing an experiment, you have to have comparison. Typically, for the most part, you compare a treatment to a control, which we'll talk about in a second. What they use terminology-wise. I would make sure that you know what a factor is and what a level is. A factor is just your explanatory variables. So in experiments, you can have more than one. In like a 2-variable set of data, you can only have one explanatory. But here, if I'm trying to see plant growth, I can have a factor for sunlight, a factor for water, a factor for fertilizer, a factor for location, and the levels are how you're changing them. So if one of my factors is water, my levels can be water daily, water weekly, water every 2 weeks. So those levels are how we break down the factor that we're changing. So just to kind of show that, all of the levels together become treatments. So one question that often gets asked, if you want to know the total number of treatments that you should have, all you need to do is multiply all levels. So we're going to do that in our first example. So in the first example, they tell us they're looking at a combination of diet and exercise. So these two things are my factors. So how they're going to break diet down is they have a group that's going to get less than 2,000 calories, a group that's going to get between 2,000 and 3,000, and a group that's going to get over 3,000 calories. So that one factor has 3 levels. And then my other factor is exercise. There's going to be a group that has 3 or less periods of exercise and a group that has 4 or more periods of exercise. So the factor for exercise has 2 levels. So to kind of describe this, I'm going to go in and say my factors and my levels. But the one thing I want to kind of point out in this question, don't feel like you're going to have to write what's not uncovered yet. I'm not going to make you. This question only asked us how many of each one. So I have my 2 factors. I identified how much or how many levels each factor had. And if I want to find the total number of treatments, all I have to do is take 3 and multiply it by 2. And that's going to tell me in total, there should be 6 treatment groups. So this question only asked how many of each one are there. Just to kind of expand on this, and I don't want you to feel like you have to write this next part down. I just want you to be able to process it and understand where it's coming from. It's a lot of writing. I don't want you to have to write it right now. With a question that asks you to identify the treatments. So if the question doesn't say how many treatments are there, instead they say identify the treatments of this experiment, you have to write out all of the combinations. So in total, I should have 6 treatment groups, and it's going to be a combo of one of the levels from diet and one of the levels from exercise. So just to show it to you, again, don't feel like you have to write this down. I went in and listed all of the possible combinations. So I just went in and started with diet first. So I listed 2 for the first diet, 2 for the second, and 2 for the third. And then I listed the 2 different exercise types after. Another option for a question like that would be a tree diagram where you can have like little branches coming off that show the 3 and then show the 2. But essentially, this is just to show you treatment groups are just a combination of the levels. So if they ask you to actually write out the different treatment groups, you're just writing out the combinations. You don't have to for this question, but that's what it would be. Okay, second and third things that we need, because I'm going to try to get through some of this a little bit quicker. Randomization. Anything in stats, you need to be random. The unfortunate thing, well, fortunate, unfortunate, is whenever you're doing a sample survey, it's completely okay to go out into the world and randomly pick somebody and ask them to do a questionnaire. Like, that's fairly normal. But in experiments, I just can't go out into the world and pick 100 people and say, okay, now you're a part of this medical study. You have to take this drug, and we're going to see if you have heart problems after you take it. Like, you can't do that to a person ethically. So because of that, we have to incorporate randomness in a different way. We have to go in and randomize how they are assigned to treatment and control groups. So instead of selecting randomly from the population, we are now going to be randomly assigning them to a treatment group. Most of the time in experiments, you're dealing with volunteers. If it's human beings, you really can't just tell people to be a part of your experiment. Now, if it's something like batteries or plants, yes, you can select randomly from the population, and you wouldn't technically have to randomly assign. But human beings, you can't force them into it. Now, one thing about experiments as well, if there is any way for you to possibly control all of the other factors, that is going to be our goal. Like, you want to, if I'm not testing sunlight for my plant, I need to make sure that all of the plants I'm looking at receive the same amount of sunlight so that that doesn't turn into a confounding variable that's affecting my plant growth. So control everything that you can. A lot of the time you also can have a control group, and that's going to serve as your baseline. So your group where if I wasn't doing anything at all, this is what would normally happen. So a lot of the time it's what they currently do. So if I'm testing a new fertilizer, my control group might just be the old fertilizer. And that's going to hopefully help reduce that variability. And the last thing that you have to have is you need to make sure that you're not just doing your experiments on one person. I can't go out for my one plant and say, okay, I gave this new plant the new fertilizer and it grew to be 10 feet tall. So because it happened for this plant, it's going to happen for all plants. You can't make that conclusion off of one thing. So you need to make sure you're using enough subjects for this to actually apply. So a lot of the time in real practice, replication can be just doing the entire experiment again and seeing if you get the same results. But sometimes that's too much time and that's too much money. So they can't always go out and do a complete cancer study all over again. So instead, they try to make sure that they're picking enough people to be a part of their experiment so that they can say these results are applicable for multiple people. So 4 things that you need for a well-designed experiment. You need comparison, randomization, you need control, you need replication. The AP exam, my test, will use these exact 4 words because they will have questions that will say they'll give you a description of an experiment and they'll say, what element are they missing? What element of experimental design do they not have? And you'll have to be able to point out like, oh, well, they don't have replication because they only did it on one person. So questions like that pop up quite frequently. So now let's get into some FRQs. So there are 3 types of experimental designs. The first one is going to be completely randomized design. So I want you to make sure that you know all of the methods we did for sampling. Simple random sample, stratified, cluster, systematic, convenience, voluntary. Those were all for observational studies. Any of that language cannot be applied for experiments. It's going to sound similar because they're the same idea of how we randomly assign is going to look the same, but you cannot use those terms interchangeably. For an experiment, it is completely randomized design. But the essential idea is the same. You guys are going to go in and you are going to randomly assign to a big group. Everyone's in one big group. I'm going to pick some random method and I'm going to assign these people in this group to a treatment. And then at the end, I'm going to compare my results from my treatment groups and my control group to each other. So one thing about a completely randomized design is you want the groups to be as even as possible. It doesn't always work out that they're perfectly even, but if you can make them even, try your best to. Don't just assign 10 people to the treatment and 90 people to the control. Try to make it 50-50 if you can. So in our case, we have an example where they are trying to see different brands of prenatal vitamins are going to affect iron levels for pregnant women. And so they're going to follow a sample of 50 expecting women. So I, in the end, have 5 different brands that I'm looking at: Rainbow Light, Nature Made, Mega Food, Ritual, and Nordic Naturals. So within my 5 groups, I have 50 women. If I'm dividing evenly, I'm going to try to find a way to assign 10 women to each treatment. So again, on your test next week, there will be a FRQ question where you have to walk me through the process of how to do experimental designs. Now, I want you to think of the dumbest person you know, just the dumbest person you know. And I want you to think, okay, I'm going to have to write this answer for that dumbest person I know, and my test grade depends on it. Like what I tell them to do, they have to get through this experiment. So a lot of the time what you'll see is I provide over details, like more than enough in any case whatsoever. They know what they should be doing. So this is going to look very, very similar to what we did for selecting a random sample for a sample survey. A lot of the randomness of it can be written the same way. The only thing you have to be careful of is with experiments, we have to kind of talk about how are we going to compare in the end to see actual results. So for the first example, and I'm going to go through 3 different ways you can do this today, I used a random number generator. So I'm going to randomly assign each pregnant woman a number from 1 to 50. Use a random number generator to select 10 integers. So again, thinking of the dumbest person I know, they're probably going to be like, well, can I pick 1.5 or 1.75? Like, no. Whole numbers, please. And we want to pick numbers from 1 to 50, ignoring repeats. Again, reiterate the numbers you are selecting from. I know it seems silly because you're literally saying to number from 1 to 50 and then pick a number. But again, think of the dumbest person you know, and they're trying to do this. We don't want to include repeats because you cannot assign a woman to more than one treatment. These 10 women are going to receive the Rainbow Light prenatal vitamin. So that is my first treatment group. Then I'm going to go in, I'm going to re-explain, now that you've picked those 10 women, how do I pick my next 10? And this one only gets to be a little bit long because there are 5 treatment groups. Whenever you only have like 2 or 3, your writing is a lot shorter because you don't have to kind of explain multiple things. For the second treatment group, I said use a random number generator to generate 10 new because I don't want them to use, and new can kind of cover a couple of bases. But again, I'm over clarifying when I give these directions. 10 new integers from 1 to 50, ignoring repeats. Technically, by saying new, you don't really have to include and numbers already selected, but I'm thinking of the dumbest person I know, and I am overstating this. I told everybody yesterday, so I'll tell you guys. I think of my brother. He's my younger brother. He's not dumb, but he acts dumb sometimes. These 10 women will receive the Nature Made prenatal vitamin. And then once I've kind of established the procedure, once it's kind of felt like it's foolproof, you can go in and say, do this for the other 3 treatments. At the end, we are going to compare iron levels of each treatment group. The one thing that a lot of people forget is the very end, the closing statement. I have graded this technically, most years, it's the question 3 on the FRQ the last 2 summers. And a lot of the time, people would write perfect randomness and then they would forget to talk about what they're actually comparing in the end. So from each treatment group, I'm going to average the iron levels, and I'm going to see what is it working for. So this would be a response for a completely randomized design. So again, think about the dumbest person you know, and you're giving that person instructions, and they have to be able to do it. It could be your sibling, it could be yourself, it could be your parents, I don't know. But the dumbest person you know has to be able to get through this without asking you any questions. You want there to be no questions about the process. So the next method is a randomized block design. With a randomized block design, this is not the same thing as stratified random sample. Yes, it's going to sound similar. You are grouping people together based on a like quality, but you are not doing stratified. With a randomized block design, basically, if there is something that is going to cause, there's two on my desk, so the two things, that is going to cause your groups to have different results. I use dogs as an example. If I'm trying to test weight loss, a diet food for dogs, I can't compare a Chihuahua to a German Shepherd. Like a Chihuahua might lose 2 ounces, a German Shepherd might lose 5 pounds. So those two numbers are so vastly different, I can't compare them to each other. So we put people into blocks, into these groups that they are similar, small dogs, medium dogs, large dogs. And then once you have blocked your subjects, you're basically just going in and doing a completely randomized design. So it's almost like you're taking your experiment and you're turning it into a bunch of smaller experiments. So instead of a big one, we have an experiment for small dogs, medium dogs, and large dogs. And then at the very end, you don't want to compare the results of the small dogs to the large dogs. You just kind of want to see, are we seeing the same thing? Are they losing weight? If they're all yes, then most likely this food is going to cause them to lose weight. So, first example, does cold water or hot water clean laundry better? They seem to think that the color of the laundry will have an effect on hot or cold water. We got 4 piles, describe and design a completely randomized block. So the first thing I did was I sorted my laundry into 2 colors, or into 2 colors, colors and whites. 2 piles for each, because they said we have 4 total. And this is going to serve as my block. And so what's going to happen is you're basically doing a mini experiment on each one. I focused on the colors block first. And so this is another example of what you can do for randomness. I have 2 options. They're either going to get washed in hot water or cold water. So since there's only 2 options, I decided to flip a coin for this one. You could still use a random number generator. You could say 1 is going to be cold water, 2 is going to be hot water. The random number generator is picking a number from 1 to 2. And that would still work the same way. So I just flipped a coin. I said assign 1 pile to be heads, the other to be tails. Flip a fair coin, and what pile comes up will be washed in cold water. The other pile will be washed in hot water. Again, I know some of this seems silly and like, why do I have to write that? If one is getting cold, obviously, the other one's going to get hot. But again, think of the dumbest person you know. And would they know that? Maybe, but probably not. So over clarify as much as you can. Now, in the end, we're going to repeat this process for the whites block, because again, you're doing 2 mini experiments, and then we're going to compare the cleanliness between the 2 water temperatures within each block. The big thing here is you are not comparing block to block. You are only comparing within the block, and then you're seeing if your results are consistent. So when I look at the colored laundry, am I doing better in cold water? When I'm looking at the white laundry, is it doing better in cold water? If it's consistent for both, then cold water temperatures are better for washing clothes. So all this block design is doing is making sure that the results are consistent even when our groups are different. So if you have an element where you know it's going to affect your results, you should block on it. Yes, Zoe?
You can abbreviate words. Can you abbreviate words?
If it seems like a common abbreviation, yes. If you're just making it up because you just didn't want to write the whole word, probably not. As long as it's understood what it should be, you can. Like without, they'll take like WO and that'll be fine. With, they'll take W/ and be okay. All right, last one, matched pairs. Matched pairs is a form of block design. Basically, this is when you're trying to test something, and usually it's human beings, and you know that there's so much variability from human to human. And you want to see if, in this case, in our example, if music is going to help with concentration. Well, everyone is so different. You have different concentration levels. You have different intellect. You have different just focus in general. And so, because everyone is so different.
Seniors, this is Ms. Clay reminding you that we have our district-wide financial aid drive tonight. Please join us in the RHS library from 6 to 8 p.m. today to make sure your FAFSA gets submitted. 6 to 8 p.m. today, district-wide financial aid night. You do not have to have your parent, just bring your laptop and make sure you have access to their taxes.
So whenever you are trying to test something and there's so much variability between person to person and you think that's going to affect your result, you can have that person do both treatments if it makes sense. Now, there's cases where we've read questions and it's like, you're going to see if peeling a potato helps boil the potato faster for mashed potatoes than not peeling the potato. That would be a situation where matched pairs wouldn't work because you can't cook a potato and then uncook it and then recook it. So most of the time you have to kind of think of logically when would matched pairs be okay. Things like this where I'm trying to see, does music affect concentration? That's something where I can have you do the same thing twice and it still seems like valid data. So in this case, they're trying to see if they complete a series of logic puzzles. Does listening to classical music and not listening affect your concentration? So I went ahead and said that each student volunteer, because again, experiments mostly are volunteers, is going to serve as their own block. And for this randomization method, I picked a hat. Hat method is like the second popular one on the AP exam that people write about. Random number generator usually is the first. But walking through the hat method. On slips of identical paper, write no music on one and classical music on the other. Put both slips of paper in a hat. The big thing, the heartbreak of the season, is if you do not write the words mix well, they will not give you credit for your random element. You have to be mixing the hat. And I will say it again when I'm picking my second option, but you have to indicate that the hat is being mixed up. For student one, because again, in most of these methods, you only have to describe one experimental block, which is what we did in the last question. We did colors. Now I'm just going to focus on student one. Pick a slip of paper out of the hat, and that will be the treatment they receive first. So whenever you're doing matched pairs design, because the person is essentially doing the same thing twice, you have to randomize the order that they get them in. So I picked out a paper. I'm randomizing which one they get first. After a period of time, they're going to get the second treatment. Sometimes for matched pairs, they can use two people who are very, very similar. A lot of the times twins can be done in a matched pairs setting because they are as alike as you possibly can be in terms of like genetics. And so they can use twin A and twin B as a pair for matched pairs. But most of the time it is one single person, place, or thing doing both treatments. So once that first person has done their first and second treatment, I can jump to the second one and I can say, okay, again, dumbest person I know. Like, yes, we know, put the paper back in the hat because I need to be picking between these two things. But I'm still going to say, return the slip of paper to the hat and mix well again. This is me being the person who graded these and had to give people partial credit despite their answer being perfect, other than the fact that they did not say mix well. And we've asked, like, everything else was great. They just didn't say mix well, and College Board said, nope, partial credit. So if you are choosing the hat method, don't forget to say that you are mixing well between your selections. Repeat the process for the other 29 students. Compare logic puzzle results for each student separately. It's the same idea as block design. You're not comparing block to block. I'm not comparing student to student. I'm just seeing, okay, I have 30 people. Did all 30 people do better when there was music playing, or did they do better when there was not? Or is it 50-50 and it's no effect at all? So make sure that you indicate at the very end, what are you actually looking at after the experiment is done? Okay. This is the basic outline of what your FRQ should look like. Now, I will say, you get to choose what random method you want to do. Do you like random number generator? Great. You only have to study random number generator. Do you like doing the hat method? Great. Only study how to write the hat method. For the coin, it's kind of dependent on the idea that there's only two options, which cannot be guaranteed, but it's not a bad one to write either. But if you want to commit to one and knowing one well, that might be your best bet for your test. Okay? Do I have any questions? That was fast. Sweet. Wonderful.